Hello everyone, I'm Enze from Peking University, and today I will introduce our paper, BFMSense, Wi-Fi sensing using beamforming feedback matrix. This is a joint work with my collaborator Dan, Jie, Fusang, Wenwei, Kai, and Daqing. In recent years, due to the pervasiveness, low cost, and non-intrusiveness, Wi-Fi-based contactless sensing has attracted lots of attention from both academia and the industry. A large number of sensing applications have been enabled, such as passive localization, gesture recognition, respiration monitoring, fall detection, and activity recognition. This Wi-Fi sensing works mainly use channel state information CSI for sensing. However, CSI can only be extracted from few community Wi-Fi cards, such as Intel 5300 and the service Wi-Fi cards through driver hacking. A recent study surveyed Wi-Fi devices in an entire city and also found that only a small percentage of these devices can provide CSI. This limitation significantly hinders the widespread adoption of CSI-based Wi-Fi sensing. In recent years, there's been a huge increase of Wi-Fi devices which support multi-user MIMO technology, driven by the popularity of the latest standards. These technologies allow the AP to communicate with multiple stations at the same time. This unique aspect of multi-user MIMO is that it requires each device to measure the beamforming feedback matrix. Interestingly, just like CSI, BFM also contains channel information which can potentially be used for sensing purpose. Compared with CSI, BFM has two advantages. The first one, BFM is transmitted without encryption. The second one, BFM is available on most new generation Wi-Fi devices. We tested 6 popular Wi-Fi routers of different brands on the market. All of them can report BFM. Thus, this offers another parameter for Wi-Fi sensing. To understand how we can collect BFM, it's important to first know how the BFM is generated during Wi-Fi communications. This involves a key procedure known as sounding. Let me introduce the key steps of this process. The first step, the AP sends the package to the station. Step 2, the station receives this package and estimates the CSI. The CSI carries the target movements information that we care about. Step 3, the station then performs an SVD operation on the CSI to adjust the BFM. The last step, the station sends the BFM back to the AP. Since the BFM is transmitted without encryption, any nearby Wi-Fi devices can hear the BFM transmission. The setup for extraction includes a Netgear Wi-Fi router, 2 10.U10 Wi-Fi cards, and a Netgear Wi-Fi cards as sniffer. We turn on the monitor mode of the Wi-Fi cards on sniffer and run Wireshark to capture the beamforming feedback packets. To generate multi-user MIMO traffic, we can use iPerf to send UDP packets, but it may not necessarily a busy network. After we successfully obtain the BFM, we want to know how to use BFM for sensing. We know that BFM is delivered from CSI. BFM can be regarded as a compressed version of CSI with some information loss. Therefore, very naturally, we ask this question: can CSI-based sensing method be applied to BFM sensing? To answer this question, let's first introduce how we use CSI for wireless sensing. For a pair of Wi-Fi transceivers, the signal propagates through multipaths from the transmitter to the receiver, such as the line of sight path and reflex path from the wall. The signals that do not change over time can be donated by a static vector HS. When the sensing target appears, a new path with varying lengths will be generated, which can be represented by a dynamic vector with changing phase. As the target moves, the dynamic vector will rotate. Therefore, we can quantify the relation between the phase of the dynamic vector and the target movements through a mathematical model. As BFM is generated by SVD decomposition of CSI, the mathematical relation between the reflection path of the sensing target and the BFM signal is not clear. The amplitude of BFM is a scaling version of the CSI amplitude. And the phase of the BFM becomes the phase difference of the CSI between two antennas. When the target is moving, compared with very nice circular rotation of CSI, BFM signals become irregular. Hence, it's not directly easy to use BFM for sensing. How to address the problem? In this paper, we leverage the multi-antenna capability to address the problem. Each antenna can report one BFM element. Through a deep understanding of the mathematical relation between the CSI and BFM, we observe although each BFM element have a time-varying scaling factor and phase offset, they are the same across multi-BFM elements on the different antennas at the same AP. Thus, if we take the division operation between two BFM elements, we can cancel the scaling factor and the phase offset. For this new signal, we call it BFM ratio. It's just like a ratio of the CSI readings from two antennas at the same AP, but it's a conjugate version. Mathematically, the ratio of the CSI readings keeps the same circular pattern as CSI, and the direction of the rotation is the same. Similarly, the BFM ratio is also a circular pattern just like CSI, but with the opposite phase rotation direction. As we can see, after taking the ratio of the two BFM elements, the irregular BFM signal pattern becomes a nice circle again. So the most properties of CSI-based sensing can still be applied to the BFM sensing. We show the BFM ratio sensing performance using two applications. The first one is respiration monitoring. Because the change of the path length induced by the respiration is smaller than a wavelength, the BFM ratio variation in the complex plane is a part of the circle. As the BFM ratio has the amplitude and the phase, we can now use either amplitude or phase to sense the respiration. Here, I show the phase and amplitude waveforms induced by the respiration in two cases. In case 1, the BFM ratio changes from A1 to A2. In this case, the respiration cannot be accurately sensed by the small amplitude change, but it can be sensed by the large phase change. In the case 2, the dynamic component rotates from the B1 to B2. In this case, respiration can be sensed by the amplitude, but not phase. From these cases, we can see that the phase and amplitude are complementary in terms of the respiration sensing. We can thus use both of them to achieve better sensing performance. We compare the performance of the respiration monitoring using BFM and BFM ratio. The results show that using BFM amplitude or phase alone results in higher errors. Combining them only slightly improved accuracy, as they are not complementary. However, the amplitude and the phase of the BFM ratio are complementary, significantly enhances the accuracy of the respiration monitoring. We also showcase the possibility of applying BFM ratio for human trajectory tracking. As the phase rotation of the BFM ratio is related to the reflect path length change of the target, it is possible to obtain the displacement information of the target. With two pairs of Wi-Fi transceivers, we can check the target trajectory. We tested different trajectory shapes, such as square, triangle, and diamond in real scenarios. We can achieve a good result with one AP and 2 nodes. Each node has only one antenna. To sum up, in this paper, we established a correlation between the BFM and human activities quantitatively, laying the theoretical foundation for BFM-based wireless sensing. Secondly, we propose the BFM ratio model, enabling the complementary sensing ability of amplitude and phase. Finally, we demonstrate the feasibility of and the effectiveness of BFM ratio for cross-grain and fine-grain sensing through 2 representative applications. We also open source a BFM tool for real-time BFM capture. That's all for my talk. Thanks for listening, and I'm happy to answer any questions.